Note at positive 10 volts, the valve is fully open and flow rate and actuator speed are at a maximum. In this case, we're assuming the pump is maxing out at 0.9 gallons per minute. Additionally, note the tiny dead band. The surprise comes when we're at positive 10 volts and we progressively ramp voltage down from 10 volts back to 0 volts. Note how when voltage is at a maximum and decreasing, the same applied voltage yields a different flow rate when voltage is at a minimum and increasing. When plotted on the way down, the flow rate as a function of applied voltage would look like the highlighted curve. This phenomenon is known as hysteresis and has everything to do with the magnetic friction I referred to earlier. Regular friction and oil impurities also play a part. Hysteresis is often specifically defined as the difference in control voltage necessary to yield the same flow rate on the way up as on the way down. For example, this particular proportional valve yields a flow rate of approximately 0.4 gallons per minute at 5 volts when it's ramping from 0 up to 10 volts. And approximating this performance curve, 0.4 gallons per minute at 4.5 volts when it's at 10 volts and ramping down to 0 volts. This is a hysteresis, or differential, of 0.5 volts. For those proportional valves incorporating spool position sensors, like LVDTs, there exists a ready means of compensating for hysteresis. The means is internal closed-loop control of spool position. Given this data for applied voltage and observed flow rate, note that a proportional valve incorporating a position sensor like an LVDT has the ability to produce an output proportional to the spool position. Assuming the LVDT also has an output of positive to negative 10 volts. On the way from 0 up to positive 10 volts, it would produce the following outputs. Fully open at positive 10 volts and allowing 0.9 gallons per minute through the valve, the spool is fully open and the LVDT produces a positive 10 volt output. On the way down, however, the spool position kind of lags behind the dropping applied voltage. A simple way of internally compensating for this hysteresis lag is to simply compare the externally applied voltage with the internally generated spool position feedback. On the way up, everything is copacetic and input directly corresponds to the desired output position. On the way down, however, there's a differential or error of 0.5 volts between applied voltage and the desired spool position. A sophisticated proportional valve can monitor this error and correct for hysteresis by causing more current to flow through the linear force motor and properly reposition the spool such that the error between applied voltage and spool position feedback is closer to 0 volts, regardless if voltage is ramping up or ramping down. The flow rate through a proportional valve properly compensating for hysteresis as a function of applied voltage would look like this. The deadband would still exist, however, flow rate as voltage ramps up is a little bit more equal to flow rate as applied voltage ramps down. By the way, a real flow rate as a function of applied voltage curve might not look as neat and linear as these previous simplifications may have suggested. A real one might observe a little wiggle waggle. However, if you squint your eyes just right, you can see the linear approximation. Additionally, these curves are constructed assuming a constant pressure drop across the valve. Proportional valves, despite their superpowers and associated expense, largely behave as would a regular flow control valve in that variations in pressure above stream or load-induced variations of pressure below stream would also serve to change the observed flow rate through the valve. Related to this phenomenon, the super observant and fastidious among you will note different flow rates for the straight-through and cross-connect positions given the same applied voltage. Not sure if you can see it, but the P to A direction is supposed to be steeper than the P to B direction. Importantly, we customarily assume this system is set up such that the cap end is hooked to the A actuator port and the straight-through position extends it. This is to suggest that a cylinder making use of a proportional valve may extend slightly faster than it retracts given an equal magnitude of applied voltage, yet of opposite polarity. This may seem counterintuitive to those of you that are versed in flow rate and volume calculations. However, it shouldn't be, because remember that flow rate through a restriction, like a regular flow control valve or a fancy proportional valve, will be greater given a larger pressure differential across it. The cap end, having a larger functional area, would necessitate less pressure to extend a given load. This means a proportional valve will experience more of a pressure differential during extension at a given applied voltage and more flow as a result. It should be noted that there exist pressure-compensated proportional valves that provide a constant flow rate regardless of variations in pressure above stream or load-induced variations downstream. Here's an example of a flow rate as a function of applied voltage chart from an actual proportional valve datasheet. You can see the similarities between it and my cartoonish simplifications. The true utility of proportional valves is only evident when they are used in combination with something I'm calling a proportional valve controller. Note the quotation marks. It's extremely hard to nail down what a proportional valve controller is because it might be some independent physical object you can hold in your hand, or it might be some nebulous invisible entity you program, and is most likely a bit of both. Case in point being our earlier discussion on hysteresis. Closed loop control of the spool position may already be integrated into the proportional valve, making the proportional valve itself part of the proportional valve controller. Another example being a PC running manufacturer-specific proprietary software used to program a proportional valve. When the program is stored in the proportional valve's non-volatile, meaning semi-permanent memory, it's disconnected. Like I said, what truly constitutes a proportional valve controller and where this boundary ends and begins is like nailing jello to a tree. For now, let's just assume it's a conceptual box that includes some pretty cool functions, only one of which I'll introduce now: acceleration and deceleration control. A brief note before continuing. Sometimes the schematic symbol for a proportional valve includes more bling than a Black Eyed Peas backup dancer. For example, here's the schematic symbol for a double proportional solenoid type proportional valve, including the internal closed loop control of spool position. Here's a single input signal where polarity determines the direction of spool movement and magnitude determines the distance. This is being internally divided by the onboard electronics into two separate solenoid signals. Here's the LVDT, and here's its feedback signal. Additionally, note that the position box of proportional valves sometimes have over and underbar lines to indicate that these are not mutually exclusive discrete positions, but rather infinitely variable. Additionally, proportional valve schematic symbols sometimes include flow control valve restrictions internal to the position boxes to make it explicitly clear that position influences flow rate. The onboard electronics may necessitate connection to a power supply, as well as a potentiometer used to adjust set points. These additional connections may or may not be explicitly illustrated on a schematic. Here's an example of an actual interface employed by a real proportional valve. The accompanying diagram tells us that pin A must be supplied continuous 24-volt DC to power the electronics internal to the proportional valve. Pins D and E are the command pins driving the linear force motor operational inside a range of positive to negative 10-volt differential. Finally, pin F is the feedback signal provided by the spool position transducer. Note this particular manufacturer is employing an analog current signal inside the range of 4 to 20 milliamperes rather than the analog positive to negative 10-volt voltage signal as I did in the previous example. But I digress. As previously mentioned, the pressure shock associated with a traditionally fully closed or fully open directional control valve can be mitigated by proportional valves by smoothly ramping applied voltage up or down over a time period, thereby slowly opening or closing the valve and suppressing the shock. This progressive increase or decrease in flow rate also directly lends itself to the controlled acceleration and deceleration of the applied load. The classic application example being the controlled acceleration and deceleration of some hydraulically operated lift, material handling system, or elevator. Ramp generators are part of the proportional valve control circuit that influence the acceleration and deceleration characteristics of a system making use of proportional valves. A ramp generator is quite simply a steadily increasing or decreasing applied voltage over a specific length of time. The shorter the length of time to reach full voltage, the more sudden and abrupt the acceleration. The longer, the more gradual and smooth. Simple proportional valve controllers may use a single slope adjustment point that controls all transitions in all directions, whereas advanced controllers may allow for independently adjustable slopes of the acceleration and deceleration ramps for both straight through and cross-connect positions. For example, this proportional valve is exhibiting rapid acceleration of the applied load in the straight through direction, and that voltage goes from 0 to positive 10 volts over a period of 1 second. It then exhibits a more gradual deceleration slope, and that the voltage goes from positive 10 volts to 0 volts over a period of 3 seconds. It exhibits similar acceleration and deceleration in the retraction direction. Note the flatline periods between acceleration and deceleration periods is when the actuator is experiencing maximum flow and moving at maximum speed in a given direction. If the slope of the acceleration and deceleration ramps were properly adjusted and the distance traveled by the actuator moving at these speeds sufficient to encompass both periods, the applied load would steadily accelerate to maximum speed and then immediately begin to decelerate. An analogy would be starting at a dead stop from one side of a basketball court, transitioning into a slow stroll, moving into a regular walking pace, picking up the pace into a brisk walk, breaking into a jog, then a run, then a full-on sprint by the time you hit center court, and then doing the exact same thing in reverse from center court to the other side. Sprint, run, jog, brisk walk, regular walk, slow stroll, dead stop. I don't know if you get this analogy or not, but I find this pretty cool. Controllers need not limit themselves to linear slopes. One can also generate something often called an S-shaped profile for obvious reasons. An S-shaped acceleration or deceleration profile might be equivalent to a dead stop, to slow stroll, to run, to sprint, skipping some of the intermediate transitions if you get what I'm saying. An example of an S-shaped acceleration-deceleration curve might be the feeling you get when an elevator starts and stops. Long story short, slowly ramping up or down applied voltage to a proportional valve rather than simply slamming it on or off at full flow results in controlled acceleration and deceleration of the applied load. This could be used to smoothly and precisely position a critical actuator without risking mechanical stress or damage. In addition to acceleration and deceleration control, proportional valves lend themselves to advanced applications, including, but not limited to, open and closed loop control of actuator speed and position, flow rate, and pressure. We'll examine these more advanced applications in later lectures. Moving on. Proportional valves are fussy, picky, finicky, persnickety beasts as fragile as an origami butterfly made out of a $1,000 bill and must be treated as such. Good filtration and proper fluid selection is essential to the proper operation and reliability of a proportional valve, and as such, systems incorporating proportional valves often necessitate stringent contamination levels and inline or pressure filters above stream of the proportional valve to protect their fragile inner workings. Additionally, some proportional valves go to the trouble of including small built-in filters. Failure to properly filter fluid or using cheaper, i.e. dirtier fluid will result in progressive loss of functionality. Additionally, proportional valves employed with actuators positioning a static load often necessitate a means of null adjustment, where null adjustment means the purposeful shift of the spool slightly off-center when applied voltage is 0 or null. This tiny shift prevents the applied load from drifting over time. Changes in temperature or pressure, or simply valve age, may cause the null position to drift slightly. Null readjustment may be a part of regular service for systems employing proportional valves. Alright, that's about it for our quick introduction to proportional valves. In conclusion, this lecture took a brief introductory look at proportional valves. We discussed how proportional valves serve to control both flow rate and direction, as well as examine proportional valve construction. We learned that proportional valves are electrically actuated, continuously variable combinations of flow control valves and directional control valves integrated in the same package that lends themselves to advanced functionality. We examined proportional valve performance data, specifically flow rate as a function of applied voltage, and discussed deadband, hysteresis, overlap, and line-to-line spools. Additionally, we examined hysteresis compensation via closed-loop control of spool position using the internally generated feedback provided by a spool position transducer known as an LVDT, a linear variable differential transformer. Additionally, we examined acceleration and deceleration control made possible by ramp generators in the controller. And finally, we discussed filtration and fluid requirements and maintenance and service procedures unique to proportional valves. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.